Hey everybody, all right, we're going to get started here. I'll try and make this as short as possible, but we are starting with 7172 ratios and proportions with similar polygons. And so one tip that I think as we do these videos that might be helpful is that if you need to pause at all to write something down, you can. I'm not really going to pause for you to do that like I would in class because it's just going to make the video longer. So I figured I'll do this and we'll try and see what you think. So I'm going to jump right in. So a ratio is, all that is a relationship between two different numbers. And so it can be 3 to 5, boys to girls, or 8 wins to 2 losses. So all a ratio is a relationship between two numbers. So I can give some examples of what that might be. For example, like I said, 3 boys to 2 girls, maybe in a class. It could be 3 wins to 7 losses for a football team. It could really be anything, but a role ratio is it just is a way to put two different numbers together. So a proportion is an equation that is set up between two ratios. So a proportion is an equation of two ratios. So you might want to use the proportion to figure something out. You might want to set up two different ratios in a proportion to solve something. An example of that would be in our Block 3 geometry class. There are 17 boys to 8 girls. So that's a ratio. In our school, we have a lot of different people, but you could say they took account of the people in our school and they said that there were 1,600 boys, for example. I'm just making a number up. So how many girls would there be? This is a proportion because there's two different ratios that are set up, and then you can use this to solve a lot of different examples that not only involve real-life examples like this, but some examples with triangles or different polygons that we do as we go forward in the chapter. So if you were to solve this, I mean, I expect that at this point you guys could all solve a proportion. So you have 17 over 8 equals 1,600 over x. You should be able to get 17x equals 1,600 divided by 8. Or sorry, 1,600 times 8. And then you should be able to solve that by dividing by 17. So if I take out a calculator and I do that, we should have 1,600 times 8, and then divide that by 17, which would say, according to that proportion, we have roughly 752 girls in the school. Obviously, this isn't true, because that would not be very even, but it shows that if we just use the proportion of the people in our Block 3 class, and we tried to say that that was the same proportion as the whole school, that wouldn't be true. So while ratios and proportions are sometimes helpful, they're not always accurate. So in this case, the ratio in our class is not accurate to the whole school. Just an example of how you could use ratios and proportions. Moving on, we've got an example here where we're going to actually use a real life example to set up a ratio and a proportion. I've got the answer down here. So one other thing that might be good as you go through these is maybe if you pause it now, try the question and see if you can end up getting the answer even without my help. So I'll go through and set up and find some information. So it says Yuva is trying to enlarge the album cover of his favorite singer, Demi Lovato, to put on his wall in his room. The dimensions of the image of the file he has are 4 inches tall by 4.25 inches wide. All right, so you've got these two dimensions. Sorry, I had to pause the video there for a second, so if there's a weird jump, I apologize. So he said he's got wall space that is 7 feet tall, so how wide can his poster be? So you've got, this is a ratio to what you have right here, that it is 4 inches tall by 4.25 inches wide. So you can set that up as a ratio. Now, I'm going to set up a proportion where I use the same dimensions for his wall, 7 feet tall, and I don't know how many feet wide I want it to be. Now, one thing that's important to mention here is I notice that my units are different. So I see here that I have units in inches and then I have units in feet. As long as the two units on the left are the same and the 2 units on the right are the same, then it's okay because they're going to cancel each other out when you divide. So it doesn't matter. If the units are different, then that's a different case, and we'll talk about that later. But the way that this is set up now, we should be fine. So if I have 4 over 4.25 equals 7 over x, I should be able to take this and set up an equation for it. So 4 times x equals 7 times 4.25. And then I would just divide by 4. So I get x equals, and I'll do this with you. So 7 times 4.25 divided by 4, that's 7.44 feet. Now, one cool trick about how you get this into an actual measurement that we can use, because nobody says 7.44 feet. They say 7 feet and so many inches. So if you take the part, so I have 7 feet, but if you take the other part, the 0.44, and you want to convert that to inches, you can just take that 0.44 and multiply it by 12, and it gives you the number of inches that it is as well. So if I do 0.44 times 12, that equals 5 inches, which is how I know that it's 7 feet, 5 inches. So it's just a good tool to know, and it's something that I really should expect you to be able to do, that you can take this and turn it into a real answer that someone in real life would use. So looks like Yu's poster would be 7 feet 7 feet 5 inches wide for his wall here. So that's one example of how you can use a ratio and a proportion. So we'll move on. So this is the part that covers the 7-2 stuff. We do 2 sections in this first part because I expect that you guys have done ratios and proportions before. So it says 2 polygons are similar if. How you know that they're similar is if all the sides are proportional and all the angles are the same. So 2 polygons are similar if all the sides are proportional and all the angles are the same. So if you want to check and see if things are proportional, you can by checking the sides. So if you know that all the sides are proportional to each other, then all the angles really should be the same. So on this case, I'm just going to deal with the sides and show you that. Because if the sides are proportional, then you know that the rest of the polygon should be proportional. So proportional sides, for example, let's put some letters on here. So A, B, C, D, E, F, G, H, I, and J. So for example, a proportional side, BC is proportional to GH. I would be able to say that, I don't know, let's use a different example. AE is proportional to FJ. So I'm setting up ratios and showing that these sides are proportional. I could throw an equal sign between them and show that they should be proportional to each other. So if I wanted to, I could say that these two are going to be similar. So I've got AE over FJ. I can show that that's true because if I plug in some numbers, BC is 3, GH is 6. Is that similar to AE, which is 2, over FJ, which is 4? And that checks out. I mean, they're both the same ratio. So I should be able to do that. So showing what proportional sides are, that is writing a similarity ratio. So I've just written one. So the fact that proportional sides would be like BC and AE, these are proportional to each other. Or sorry, the other way around. Proportional sides, BC and GH are proportional to each other. So those are an example of proportional sides. A similarity ratio is the entire thing that we just wrote. So again, another example of a similarity ratio would be that IJ over DE, so this side and this side, should be proportional to JF and EA. So this is the ratio, the fact that you're setting up those, you're showing that they're similar. So this whole thing is a similarity ratio. This whole thing is another similarity ratio, and I wrote a proportion to show that. So the ratio is just the piece, and the proportion would be setting them equal to each other. So I know that they seem similar. Again, the ratio is just this one thing right here. And proportional sides, 2 sides that are proportional to each other, I've shown you as well. So Congruent angles, I could say that if these two things are proportional, then I would be able to say that, for example, angle A is congruent to angle F. That would be an example of congruent angles. If I wanted to make a similarity statement, I could say that these polygons are similar, so that polygon BCDEA is similar, and the symbol for similar is that little tilde right there. And that should be similar to GHIFJ. So I'm just going to put it underneath GHIFJ. So those are similar to each other. So we'll do more of this practice and stuff in class with writing these out and showing that they're similar. Really, the end goal is to do this with triangles, and so that's why we're doing this. But I just wanted to show you some of the vocabulary so that you could see what some of the vocab comes out to. If you want to, you can always check some stuff in your book as well. If you go online and you look at 7.2 and you take a look at the book pages, you should be able to see what some of these examples are. And if you want to see some more of the vocab, you can see it in here. So there's more examples of similar polygons. If you scroll the next pages over from there, you'll be able to see some more examples of this as well. And they've got, an example here of a model like we did, like we're going to do, but then they've also got a similarity ratio. So they're showing that those ratios are what we were just looking at as well. So I just wanted to show you that those are out there and they're available, and that's what they are. So just to add on to that similarity ratio, you could get the numbers, and so the ratio between these two numbers would be 4/2, which would be 2. So that's another way, if you want to write the ratio between the sides, that's really the end goal for that, is getting to the fact that the ratio is going to be 2. Whereas if you're showing the sides are proportional, you're just writing out the sides. So anyways, let's move on from there. I believe that this is the last large problem I want to look at. Just a time check here. So this is the last large problem. I've got one other one that I want to show you how to do as well, really quick, and then that'll be it. So I like using Matchbox cars as an example because unlike Hot Wheels, Matchbox cars are actually to scale. So I just Googled what the dimensions were of a Mini Cooper, and I came across this image, and we'll go through it. Again, try this out on your own. See if you can do it by yourself. It'll take you, an extra minute or two to try, but you might as well try it out. So I've got these two different examples. It says Matchbox is a producer of miniature cars that are still to scale. Mr. Walk's Mini Cooper is 12.19 feet long. This is accurate. And if the scale Matchbox uses is 1:64, how long will the toy car be in inches? So I need to be able to set up a ratio from my car down to a miniature car. And so the length of my car over the length of the miniature car. So I'm just going to put the length of my car over the length of the Matchbox. I should be able to set that up and use this scale. So 1 obviously is going to be the length of the smaller car, and 64 would be the part that goes with my car. So I would set that up as 64/1. You could flip it, and if you had set up the length of the Matchbox over the length of my car, obviously it would just be the same thing, just flipped around. So if I plug in some numbers, the length of my car is 12.19 feet over the length of the Matchbox, which I don't know, and then the scale, which is 64/1. So if you set that up and solve it, you get 12.19 equals 64x. You divide by 64, and once you divide that by 64, you get 0.19. So even though that number seems a little bit strange, that's in feet. You have to remember that that's not such a strange answer. If you take that, now I want to be able to find this in inches because that's not really helpful to anybody. If I multiply this by 12 and get it into inches, it's about 2.29 inches. So times 12 equals 2.29 inches. That's the answer that you want. That's what's actually going to be helpful. So if you have a hard time with conversions and stuff, then we're going to maybe need to work on that this chapter. Here, I'll get rid of this for now. But that's one example. So the next one's a little bit tougher because it has some conversions. Again, I would suggest that you pause it and try this example so that you can see how you would do. But I'll show you how to do this one. So It says, since Mini's a German designed car, the measurements are given in millimeters. If the car is 1,407 millimeters tall, how tall will the scale model be? And I gave you a conversion so that you can use this. But the beginning of this problem is going to be the same as the last one. So it's going to be the height of the Matchbox and the height of my car. Notice that those are reversed from the last time. It's okay. It's not a big deal. You can set it up either way, so it's fine. That should equal, now the Matchbox is the 1, and my car would be the 64, so we have to use the same proportions. So the thing is right now I'm in millimeters. So I'm going to take it for granted that you know how to convert millimeters to centimeters, because my conversion over here, the 1 inch to 2.54 centimeters, is I got to be in centimeters first. So millimeters to centimeters, you move the decimal place once. You know, the King, Henry, there's some way to remember it. I don't remember off the top of my head. But this is 140.7 centimeters. Now I should be able to convert that to inches. So I'll take the 140.7 centimeters. I'll divide that by 12 centimeters. Or sorry, what am I dividing by 12? I'll divide that by 2.54 centimeters in an inch, and the centimeters will cancel. I don't know that off the top of my head, but let's check. Divided by, it's about 55.39 inches. All right, so I want my eventual answer in inches, so I'm not going to bother converting that to feet. Or do I need to? Let's see. I've got the height of my car is in feet, so I might need to do that. So I might as well just convert it to feet so that it matches. So if I divide that by 12, I've got it 4.62 feet. So you could do it in feet. You could do it in inches, actually. So I'm just going to keep it in inches. But if you had done it in feet, then that's how you know what it would be. But if you didn't do it that way, then that's fine. So I'm going to set up my proportion now using this here. So the height of my Matchbox is, I don't know what that is, but the height of my car is 55.39 inches. That equals 1 over 64. And now setting that up and multiplying is the same as before. So you get 64x equals 1 times 55.39. And if I divide by 64, 55.39, oops, divided by 64 equals 0.87 inches. So it's just 0.87 inches tall. I mean, there's nothing you can do with that. It's less than an inch. I mean, these things are small. So you can get an answer less than 1. You know, go look at a ruler. 8,707 isn't all that small. But it's about the size of a Matchbox car. So this is a good word problem example. I would expect you to be able to do a question like this after we spend some time practicing in class, because this is a really good application of ratios and proportions. There's one other example that I wanted to show you how to do, just so that you can do one with the sides of a triangle. So there was a bonus like this on a test, and I realized that I didn't include a slide on this. So all that it's asking you to do is, you know, if the ratio of angles in a triangle are, say, 2 to 3 to 7, what are the angles? If you know how to do this already, just stop the video and you're done for the day. But if you don't know how to do this, then stick around for the next minute or so I can show you how to do it. The angles should add up to 180. And this ratio means that there's some number that I multiply these all by, and I can get each angle. So that, I don't know what I need to multiply, but I'm going to multiply each one by some number x, and those should add up to 180. 2 and 3 is 5, and 7 is 12. X equals 180. If I divide by 12, 18 divided by, I don't know that off the top of my head. I should, though. 180 divided by 12 is 15. Here, let's move this. So that means x equals 15. So in order to get the three angles, I take them and I plug them back in. So 2 times 15 is 30. 3 times 15 is 45. And 7 times 15 is 105. So the three angles would be 30 degrees, 45 degrees, and 105 degrees. Just wanted to show you one of those. That way you were good to go there. All right, that's it. Hope you enjoyed the first one. I don't know how long it was, 20 minutes, and that's about it.